Hello everyone, I'm Yudin. I work at Netease Fuxi AI Lab. I'm so happy to introduce our work on generating full-body animation for a talking NPC. Firstly, let me introduce what the problem is. First, let's look into the existing methods and their limitations. Traditionally, animation trajectories are created manually by experienced artists. A 10-second animation often takes 2 days or even 1 week. Recently, with the development of motion capture techniques, making a 10-second animation takes half a day, including data capturing and correction. Both manual creation and motion capture are time-consuming. Hiring experienced artists and building mockup systems are both quite expensive. Moreover, the created animations can be only applied to planned scenarios. Traditionally, we often reuse the handcraft or motion capture data by concatenating the existing animation clips. These methods result in repetitive animations and lacks variability of animations. Another problem is how to select a fitting interpolation function to bridge two animation clips. An interpolation function may perform well on a few of animation clips, but fail on others. Moreover, the interpolation function damages and misses the subtle animations. Observing this existing method and their limitations, we think whether it is possible to automatically generate the full-body animations. Specifically, our work attempts to develop an animation generator for NPCs who are talking. Our aim is to reduce the time consuming of making animations. We make efforts on creating high-quality animations. The high-quality animation should be natural, lifelike, and human-like. They are able to convey appropriate emotion and intention. They are variants instead of repetitive patterns. In our current work, a 15-second facial expression is generated in less than 6 milliseconds. A piece of 20-second body language is made within 600 milliseconds. Our work has been applied to several games developed by Netease. Let's think about what happens when we are talking. What happens to our comportment? Indeed, amount of academic researchers have reported that our behaviors can emphasize ideas, signal syntactic boundaries and stress, complement verbal information, and also express emotions and intention. On the other hand, while speaking, human facial and body behaviors are closely related to simultaneous speech or spoken content. This inspires us to think about synthesizing animations according to the input speech. Our solution relies on neural networks to perform the mapping from speech to simultaneous animations. The neural network learn and capture the temporal relationships between human behaviors and speech. In the stage of computing animations, the neural network takes the speech as input and synthesizes the animations, while rendering the learned temporal relationships into the generated animations. As known, training neural network requires amount of data. To obtain adequate data, we use an optical motion capture system, VICON, to capture body movements. and use dynamic XYZ to capture facial expressions. In our work, lip and jaw movement are represented with 28-dimensional vector at each frame. Eyelids and eyebrows together with 22-dimensional vector, and 76-dimensional body movement. The motion capture process ensures the high-quality data. To better display data, we manually make retargeting to reduce the effect of skeleton and face gap between actors and targeting NPC. The training data consists of amount of pairs of simultaneous speech, facial expressions, and body languages. Each pair refers to an utterance. And let's make T represent the audio length time frame. The lower facial expression is represented with a 28-dimensional animation sequence lasting T time frames. The upper facial expression is represented with 23-dimensional animation sequence lasting T time frames. The body is a 76 animation sequence lasting T time frames. Let's talk about a lower facial expression first, involving lips and jaw. I think some of you may be familiar with this topic. Reviewing most of the published work, speech features are often used as input to synthesize mouth animations. Of course, speech features contain full information. On the other hand, speech features keep some information that is not related to animations. For example, speaker-specific timbre is included in speech. It cannot reflect any information related to animations. If speech features are disturbed with speaker-specific timbre, these speech features damage the quality of synthesized animation. Of course, we may ask questions that we can use speech features which have left out speaker-specific timbre. We are also making efforts on refining speech features disentangled from speaker-specific timbre. Okay, now let's move to a useful solution instead of using speech features. We propose to use text information for mouth movement. We propose to use the uttered content like phonemes. Phonemes are absolutely non-related to speaker-specific information. It is very easy to extract phoneme information with the speech recognition tools from human speech. If using syntactic speech, phonemes can be obtained directly from the TTS. And here, I emphasize one more detail. Once we get the phoneme sequence from a speech, we have aligned phonemes according to their duration. Specifically, we repeat the phoneme label according to each phoneme duration. Like this, we can get time-aligned phoneme sequence. To facilitate computing, we set this phoneme sequence at the frequency as same as motion sequence. This slide demonstrates an example. Oh yeah, you don't know to tell me where she is. Then, according to the audio, ASR helps us recognizing time-aligned phoneme sequence here. As observed, the phonemes are repeated according to the lasting time of phonemes. As mentioned, neural networks are used to capture temporal relationships between time-aligned phonemes and mouth animations. Intuitively, we take into account ASTM, that is typical neural network modeling temporal relationships. In fact, amount of researchers rely on ASTM to process temporal relationships and have successful experiments. On the other hand, ASTM is a recurrent model. It computes the output sequence frame by frame. The next frame output depends on the output of its previous frames. It is time-consuming. Therefore, we attempt to use another neural network structure, CNN, convolutional neural network. The CNN performs the calculation with the parallel computing. In our experiments, for a 15-second sequence, while ASTM takes 500 to 800 milliseconds, the CNN takes 20 to 60 milliseconds only. And this slide shows our neural network framework. This input is time-aligned phoneme sequence. Here. Time-aligned. We repeat the phonemes according to the lasting time of each phoneme. And our work relies on 12 layers. And each layer is residual layers. And the output is 28-dimensional sequence, which lasts T frames. Specifically, T is 30 frames in our work. The training data consists of 865 utterances, each lasting about 5 to 15 seconds. And here, I show you a few results by comparing syntactic and motion capture leaps. In total, I show you 4 comparisons. In each comparison, the left one is animated with syntactic data, while the right one with mocap data. Okay, I will show you the first one.
我的妈呀，吓死我了！
I repeat it again. You can observe the lip movements.
我的妈呀，吓死我了！玩个游戏而已，拉黑就没意思了。玩个游戏而已，拉黑就没意思了。其实不想失去，才不想再拥有。其实不想失去，才不想再拥有。再三犯错，你说气不气？再三犯错，你说气不气？
Okay, so you can observe that both animations are so closely to each other. And we extend the lip motion framework to generate photorealistic mouth movement. We can find that it's difficult to distinguish the syntactic and ground truth talking mouth. Okay, let's have a look.
Why didn't Randall tell me the gun was loaded? He's my friend. With my luck, I could have killed someone.
Once again.
Why didn't Randall tell me the gun was loaded? He's my friend. With my luck, I could have killed someone.
And now, let's move to upper facial expression involving eyelids and eyebrows. Similar to lip expression generation, I repeat 2 tricks, using time-aligned spoken words instead of using speech features. I emphasize here, different from lower facial expression using time-aligned phonemes, the upper facial expression generation uses time-aligned words. This slide shows the neural network framework for upper facial expression. The input is a time-aligned word sequence. The output is 23-dimensional animation sequence, which lasts t frames. This frame is a typical encoder-decoder. The encoder is colored with yellow. A decoder with green. The encoder extracts meaningful information from text into a latent representation, and then the decoder translates this latent representation into the output animation sequence. The training relies on the 50 minutes data. And here, I repeat the above comparison results. This time, let's focus on the upper facial expression.
我的妈呀，吓死我了！我的妈呀，吓死我了！玩个游戏而已，拉黑就没意思了。玩个游戏而已，拉黑就没意思了。其实不想失去，才不想再拥有。其实不想失去，才不想再拥有。再三犯错，你说气不气？再三犯错，你说气不气？
As observed, the syntactic and mockup data are also close to each other. And here, I show you a clip from our game Justice. In this video, the facial expression is automatically generated from the above-mentioned framework.
戏也该散场了。
你若恨我，活着报复我，不是更好？
爱很苦，恨也很苦，我都不想要了。
Okay. And here, this clip shows you the example from another game named Revelation.
好呀，等你身体好一些，我们就
不要紧，我今天觉得好多了。
Okay. Thirdly, let's talk about body language generation. For body language, we use MFCC. The solution relies on a common used neural network UNet. The output is a 76-dimensional animation sequence, which lasts t frames. The use of UNet benefits from achieving large receptive field with little computational cost and better capturing multi-scale features. The training relies on the 10 hours data. And here, I show you a few examples of generated animations with different emotions.
傻孩子，江湖太盛大，也太复杂。傻孩子，江湖太盛大，也太复杂。你怎么知道我喜欢他的了？谢谢你。你怎么知道我喜欢他的了？谢谢你。这歌声是秦姑娘，可她在哪儿？这歌声是秦姑娘，可她在哪儿？傻孩子。
And here I show you a few examples of generated animations with different styles of NPC. The first one.
别说了， 说得我心里好难受。别说了，说得我心里好难受。你别说了，说得我心里好难受。你别说了，说得我心里好难受。你别说了，说得我心里好难受。你别说了，说得我心里好难受。
In these videos, the full body animation, including the full facial expression and the body languages, are generated with the mentioned above frameworks.
别说了，你别说了。
And here, it is a virtual tutor that is used in a popular online application of learning programming. It is called Code Combat.
其实呀，我们在读书的时候多想想，不懂的时候多提问，就会发现更多好玩的知识。其实呀，我们在读书的时候多想想，不懂的时候多提问，就会发现更多好玩的知识。太棒了！我就知道小小的难题难不住你。太棒了！我就知道小小的难题难不住你。你看看人家班，年年都是学校第一名，你再看看我们班。你看看人家班，年年都是学校第一名，你再看看我们班。其实呀。
And here, it is another application of virtual tutor. Given edited text, while TTS helps us for generating syntactic speech, our framework generates animations. Let's take a look.
丑小鸭去了许多地方，在哪里都不被大家喜欢，没有小动物愿意跟它做朋友。虽然丑小鸭难过，但它却没有因此自暴自弃。最后终于找到了接纳自己的同伴们，我可真佩服这样勇敢的丑小鸭呀！丑小鸭生来就跟其他鸭子们不一样，但是不一样也没什么不好。你知道吗？地球上有77亿多人，但是我们每个人都是不同的，每个人都一样重要。为什么这么说呢？一起来看看吧。丑小鸭去。
So, our work demonstrates that AI helps animation generation. For instance, a 10-second animation is automatically generated less than 60 milliseconds instead of manual creation with a few days. So, while speaking, it exists correlations between human behaviors and speech. And human behaviors are temporarily synchronized with the prosodic and syntactic structure of the speech. The deep learning techniques compute correlations between human behaviors and simultaneous speech. Neural networks are powerful for the automatic generation of body animations according to the input speech signals, or we say the speech-based information. With the neural networks, the face or body animation generation requires the time consuming in less than 60 milliseconds for facial expression and 600 milliseconds for body animations. So about the limitations, there is still a long way to go in making the generated animations more expressive. There will always be a need to retarget the output animations to NPC with different skeletons. The frameworks require high-quality motion capture data. The styles of generated animation depend on the recorded dataset. About the feature work and how If we'd like to improve the quality of animation, we have to take into both the text and audio information for making the expression and the behaviors more believable and more human-like. But that is it is a challenge. How to model the interaction between the text and audio information in order to generate high quality animation. And in the future work, we will take into account inherent correlation among the three modality animations, including the upper facial expression, lower facial expression, and body language. And we will make more the facial expression, and the body language with more semantic informations. And thank you. This is my talk.